Dear colleagues, good afternoon to our Chinese colleagues and participants, and good morning to our Israeli participants and colleagues. I am Professor Itamar Vilner, member of the Israel Academy of Sciences. I am honored, together with Professor Yulang Zhao, member of the Chinese Academy of Sciences, to act as co-chair of the bilateral webinar meetings in the field of nanotechnology. The Israel Academy of Sciences and the Chinese Academy of Sciences have long-term scientific collaborations and cooperations reflected by many mutual scientific meetings in various fields, exchange of scientists, students, and most importantly, superb friendship. Israel praises the advances in science promoted by the Chinese Academy of Science and values the scientific relations and collaboration between the two academies. 2 years ago, we decided to host in Jerusalem a bilateral meetings between the two academies in the area of nanotechnology. But unfortunately, due to the corona pandemic, several delays to organize and conduct the frontal meeting were experienced. And we decided to realize this effort by conducting a series of 4 webinars in several subtopics of nanotechnology. Due to the time differences between China and Israel, we were forced to limit the number of lectures to 4, and we realized that many of the scientists in both countries are disappointed from not being able to present the research. Yet I understand and hope that the participants from both countries will understand these limitations, and we will be able in the near future to compensate for these difficulties. We have 4 subtopics that will be covered by these webinars. The first one took place 2 weeks ago. It was on nano devices and nanophotonics, and it had a great success, and the responses were very positive. And today, our meeting will be on the topic of energy and environment. I have to say that the organization of this meeting needed to overcome many obstacles and difficulties, and I would like to thank the co-chair, Professor Zhao, Dr. Xiao from the Foreign Affairs of the National Center of Nanoscience, and Ms. Zhao, the program officer from the Bureau of International Cooperation of the Chinese Academy of Science for their continuous help to organize this meeting. I would also thank all the chairperson, the moderators, the speakers, and the organizing committee that had to, in Israel and in China, to organize these 4 webinars. Particularly, I would like to mention the staff of the Israel Academy of Science that Miss Galia Finzi, the director of the Academy, Joe Cohen, that you saw her on the screen several times, the director of international relations, Naama Shiloni, the head of public relations, Yaakov Rotman, who is the computing leader of the computing department of the Academy, and Mr. Arik Futterman, the technical production officer of these conferences that you met him already at the introduction. Last but not least, I would like to thank Yael Ben Chaim, the secretary of the science division of the Israel Academy, for her daily efforts, including yesterday and the day before yesterday with all the changes, in organizing these webinars. Her contributions are certainly significant and invaluable to the success of this webinar series. On behalf of Professor Nili Cohen, the president of the Israel Academy of Sciences, I'm delighted to open the second webinar on energy and environment, and I wish all of you a stimulating scientific experience during the day. I would like to invite Professor Zhiyong Tang, the Vice President of the National Center for Nanoscience and Technology of the Chinese Academy Center, to have his greeting and to represent Professor Zhao that could not participate due to other activities. Thank you very much and good luck.
Dear Professor Itamar Werner, dear Israel colleague, good afternoon. On behalf of our director, Professor Yuliang Zhao, let me welcome to everybody join the Israel-China bilateral series in nanotechnology. China and Israel has made the first achievements in practically cooperations in the fields of nanoscience and nanotechnology. The platform construction have been pushed continually, and the friendly exchanges have been intensified consistently. The cooperations has displayed fruitful highlights in talent cultivation, bilateral meeting, and the joint project application. The Israel-China bilateral series in nanotechnology mainly focus on the latest progress and the future development trend of nanoscience and technology, especially the preparation, characterization, application, and development trend of various nanomaterials, nanostructures, and related nano devices. It provided a high-level exchange platform for the scientists in the field of nanotechnology and laid a solid foundation for long-term exchanges and collaborations in the field of nanotechnology between China and Israel. I hope that such collaborations will provide outstanding opportunities for academic exchanges, technology innovation, discussions on the future prospect, exchange of the people, and share our research policy as well as the resources. Finally, I wish a great success of this conference. Thank you.
Hello, it's my turn to introduce the first speaker. Hello, good afternoon. Here is Xiaochun. I'm very glad to introduce our first speaker, Professor Zhixiang Wei from our center. I first give a short presentation of his research activity. Professor Wei's research interest is focused on self-assembled organic functional materials and flexible energy-related devices, including solar cells, sensors, and batteries. He received his bachelor degree in 1997 and master degree in 2000 from Xi'an Jiaotong University. Then he received his PhD degree in 2003 from the Institute of Chemistry, CAS. Later, he spent 3 years abroad. In 2006, he joined our center as a full professor. Professor Wei has published more than 150 papers and has been awarded numerous honors. Today, Professor Wei will give a talk about organic nanostructures for flexible solar cells and energy storage devices. So now welcome Professor Wei for his talk.
Yeah, thank you. So can you see my slides?
Yes, we can see.
Okay, great. Thank you, Professor Wu, and thanks Professor Zhao and Professor Wheeler give this really great opportunity for this bilateral conference in nanotechnology. Yeah, in the past years, actually, I working in the organic nanostructures, especially their application in energy-related devices. Today, I will talking about our efforts on organic structures for flexible organic solar cells and organic energy storage device, mainly made in the last 5 to 10 years. Yes, as we know, actually, we are living in a world, actually, the wearable electronics becoming more and more important. Yeah, we see the trends of the industry developing different kind of the wearable electronics. Sorry, the different wearable electronics, including the sensors and also different kind of the energy-related devices. For our efforts in our laboratory, we're working in different aspects of this kind of the flexible structures, especially in the organic solar cells and flexible lithium-ion batteries. And in the future, actually, we want to really integrate all these kind of structure to get the flexible energy system. Yeah, if you want to make the flexible device, normally there's two strategies. One is I call the inorganic strategy. You can making the flexible device by making them smaller and link them with a flexible substrate. Therefore, actually, for example, this kind of the armors, also this kind of OLED, LEDs, you can making some flexible device. The second is organic strategy, for example, electrolysis and some OLED, because they are using the organic material. In principle, this kind of material is flexible. Therefore, organic strategy might be a better way to making more flexible device. Today, my talk will divide into two parts. The first is on the flexible energy storage device. How can we really making this kind of flexible device by optimizing their nanostructures and hierarchical structures? The second one is this kind of flexible organic solar cells. How can we develop some new material, develop some new formulation And then by combining the printing method, we can making this kind of the same flexible organic solar cell with high efficiency. Yeah, the first part is a three-dimensional hierarchical structures for energy storage device. Yeah, why we need energy storage device? Because actually every day we need to power our flexible device for the sensors, for example. Therefore, actually we need high capacity and high rate performance for energy storage device. And nanostructures might be efficient way to tuning the structures or electrode material. With this way, for example, just like the cartoons, actually you can optimize the ionic and also electron transport pathway, then you can improve the performance of the electrode material with high performance. And with this one, we can assemble some flexible batteries with high capacity and high rate performance and also flexibility. For example, the supercapacitors, lithium-ion batteries, and lithium-sulfur batteries. I just named a few examples in our research. Our starting point is back to 10 years ago. We found this kind of the nanostructures. This is kind of the conducting polymers. The kind of conducting polymers actually they are really good material for supercapacitors. If we're making these kind of nanostructures, actually their performance even better. They can approaching the theoretical capacitance of this kind of material, and they showing really high rate performance. That means you can charge this charge with high current density, and their capacity decrease very small. But how can we really get the real electrode material? This we need to considering this kind of three-dimensional structures. First, we combine this kind of the nanowire arrays with two-dimensional material using graphene or graphene oxide. We can group in these kind of nanostructures in these two-dimensional materials, get this kind of hierarchical 2D, 1D nanostructures. And with this one, you can see not only their capacitance, but also their stability really increased comparing with the traditional disordered nanostructures and also their single component of the graphene oxide. With this one, actually, we can get the material with high capacities, high stability, and scale-up synthesis because their synthesis are easy. Just mixing the aniline monomer with this graphene oxide in solution, by oxidization, you can get this kind of structure. This is actually was selected as the 10 most important papers in SS Nano in their 10 years celebration. And how can we really making the flexible device using this kind of nanostructure? Yeah, actually, for example, we can making the self-supported porous graphene. Yeah, by this kind of template because it's using this calcium carbonate template, we can remove this template, we can get the porous structures, and we can then group this kind of polyaniline nanowire arrays in this porous. And finally, we can get this kind of the film really with good shape and good flexibility. And also if you, yeah, this is a pure graphene, and then you can group the polyaniline on the surface, inner surface, you get this kind of hierarchical structures. With this one, we can really assemble some flexible supercapacitors. You can see we just stack two layers together, and this kind of flexible supercapacitor showing really good cycling performance with different bending angles from 90 degrees to 100 degrees, 180 degrees. And also you can see still have really good capacitance and also high rate performance. That means you can charge this charge with high current density, and the capacitance are kept very high. With this strategy, actually, we can produce different kind of material for different kind of applications. For example, in the lithium sulfur batteries. Yeah, for this kind of structure, we can group the polyaniline nanoarrays in these three-dimensional pores. And by different kind of the thermal treatment like pyrolysis, we can get the three-dimensional reduced structures of the nitrogen-doped carbon. And this kind of non-nitrogen carbon, actually, by this kind of the filtration, you can changing their vertical direction distribution. In this way, you can purposely design some material for the lithium metal or for the sulfur electrode. Therefore, using this one substrate, we can assemble the full lithium batteries. You can see it's showing really high capacitance and also high stability. And these batteries are flexible because all these kind of substrate are flexible, and we can really making these kind of flexible lithium sulfur batteries. Recently, not only for the organic structures, we also using these structures to extend to the inorganic ones. For example, recently we used the copper foam to making this kind of three-dimensional copper oxide material, using this substrate to glue this kind of the copper oxide nanowires. This kind of nanowires actually can regulate the ion and also the electron transport pathway, and therefore actually you can get a really good material for lithium metal electrode. Yeah, this is a performance, and if you don't use the hierarchical structures, just using copper as the porous copper as the electrode material, actually because the lithium nucleation is ununiform, you get lithium dendrite. Therefore, the performance is really poor. But if you're using these kind of hierarchical structures, the lithium nucleation and lithium growth is quite smooth. And finally, you can get a really good material with high Coulombic efficiency at different charge discharging speed. You can see this material actually much better than reported material using different other kind of strategies. And also we can combine this strategy with organic electrode. For example, this is a cathode material for the lithium ion batteries, and we can combine these carbon tubes and graphene with this material and can assemble this kind of flexible organic lithium batteries. With this knowledge in hand, we ask our question, we can really assemble a battery that can meet the requirement for the industry. Therefore, actually, we starting from material, also we design some kind of the architecture or different shapes of the batteries, and finally we can demonstrate some flexible batteries that can meet the requirement for the industry. Yeah, for the real lithium flexible lithium battery, not only the electrode material, but the current collector is also important. For example, in the commercialized batteries, they use the copper foil and aluminum foil as a current collector. But this kind of metal foil is not that flexible. We can replace this kind of metal foil with a copper-coated cloth or this kind of carbon nanotube film. They are highly flexible. And with this one, we can assemble some batteries with, for example, these are thin batteries and can show you really good flexibility. You can even bend them and also folded them. There's no decrease in the capacity and also the voltage. But the question is, if you're using the battery, normally you need their high capacity. That means this kind of thin battery, the capacity normally not that high. But if you're making the battery thicker enough, normally there's some problem on the mechanical properties. For example, in the thick films, if you're using this kind of materials, because the outer side is a tensile strength, inside is compression strength. There will have some cracks on the inside surface. Therefore, we design these wave-like structures and find that they are really good to showing this kind of flexible battery with high capacity. This is the real image. This is the traditional batteries. yeah, we can see it, yeah, can bending, but after some bendings, there's some cracks on different side. But this one, you can bending in different cycles and showing almost no changing in the performance. And we demonstrate this kind of the application of this flexible battery can use in different kind of application. For example, the band of the smart watch, and even some smart shoes, and also some band in the night. And recently, by combining different kind of materials, actually we can showing this kind of really good flexible batteries. We use all the material are flexible, and using some special structure design strategy I didn't show here. But anyway, can making a thick battery with about 1 to 2 nanometer, 1 to 2 millimeter thickness, and the total capacity about 200 milliampere hour. Actually, this already meets the requirement for real application. Yeah, this is a story for the flexible batteries. Then I showing the second topic in the printing large area flexible organic solar cells. Yeah, organic solar cells is a strategy that can making solar cells with much easier production process. Traditional battery, silicon battery, for example, they use the single crystal silicon and then cut them and doping them, and then you get the silicon solar cells. But for the organic solar cells, you get the P-type of material, N-type of material. They are solution processable. And in this, using this solution, you can spin coating or solder coating in different substrate. And finally, you can get the flexible solar cells. With this one, actually, this kind of mechanism are different from traditional silicon batteries. We're working on that also. And the more interest is this kind of strategy is actually matching with the roll-to-roll printing technology that can printing large area flexible batteries. I will show you this one. And organic solar cells, actually, at the beginning, their efficiency is quite low. But in the last 10 years, especially in the last 2 years, driven by the material innovation, actually you can see their recognized efficiency actually certifies the efficiency actually increased quite fast. Now it's approaching 18 or 19. Yeah, this are already not far from the traditional batteries. For example, single crystal silicon, the efficiency is 26. The shock frequency limit for the single junction solar cells is 30%. Therefore, actually, there are really big requirement from, for example, in the laboratories, people want to pushing this kind of technology from a small area to the large area printing. Yeah, we write a review two years ago, but if you see the efficiency, normally, if you're doing the small area rigid substrate, normally efficiency is high. But if you're doing the large area rigid or large area flexible, you see their efficiency actually decreased a little bit, especially in the large area flexible ones, it decreased a lot. Therefore, yeah, you can see the power conversion efficiency decreased from the lab scale to the large area scale cells and modules. So this kind of decrease is from different kind of losses. For example, yeah, there's some electrical losses from the transparent conducting film and also the active layers, and also the geometric losses due to the actually dead area that not contribute to the efficiency, and the optical loss mainly because of the film are not uniform. And also some additional losses, for example, in the lab scale, you can use some really poisonous solvent, but for the industrial scale, you need to use some green solvent. At least you need to use some toluene or xylene as a solvent, not use the chlorobenzene. Yeah, with this one, actually, the efficiency normally decrease a lot. Therefore, from 5 years ago, we started thinking about this system. We find a really good strategy we call the ternary strategy that can really increase the efficiency and keeping the material have a good solubility in the common solvent. Yeah, this one actually we use a small molecules to increase the crystallinity of the polymers, and then you can get a really good alloy of the small molecules with polymers, and really showing this material after combination with different kind of the materials. Actually, we showing the first PCE higher 10 in the ternary solar cells. The reason is after adding the small molecules, actually we increase the crystallinity of the active layer, and this you can see the pipette stacking actually are increased. Therefore, their charge transport are better. With this, we can comparing with the binary and the ternary system. Using binary, normally the efficiency is reasonable at 100 nanometers. But if you increase the thickness, because of the loss of traps in this active layer, the efficiency decreases very fast. But in the ternary stage strategy, because of the crystallinity are much better, their thickness are not that sensitive to the thickness. Therefore, actually, it's quite good for the large area fabrication, because in the large area printing, you cannot printing 100 nanometer scale really precisely. Yeah, therefore, actually, we can show you if we making the 1 centimeter square flaccid device by spin coating, we can get the 7% in the binary, but 8% for the ternary. You can see the every curve are quite good. And then using this strategy, we can combine this kind of ternary strategy with roll-to-roll printing. In the industry, they normally use this kind of slot die printing. Using this slot die printing, actually you print this kind of active layers in the substrate, and then you can integrate this kind of different subcells by in series or in parallel. Finally, you can get a solar cells just like that can really power the electronic devices. And therefore, actually, you can see we can using a small area device is about 4 millimeter square, efficiency about 10. But for the large area, for example, this one line actually is 5 centimeters square. The total is 25 centimeters. The efficiency is close to 6. The decrease is quite obvious, right? Therefore, in the next few years, we actually thinking about this problem to thinking about whether there's better system really can showing they can decrease the PCE losses from small area to a large area. We find this system actually is invented by one professor in our center, Professor Li Mingding. And we use this system, we combine some really good conducting substrate is a silver grade, and is showing high conductivity and high transparency. With this one, if in the small area by spin coating, the efficiency about 12. The solution, the solvent is sealing, and in the 1 centimeter square is about 12, almost no decrease, right? Yeah, this is blue and red point, and then we can further enlarge the areas and into 5 centimeters square to the 25 centimeters square to 50 centimeters square. The efficiency decreased a little bit, but not obviously, but it's in the 50 centimeters square. It's really decreased because our printing technology is not that good yet. Yeah, therefore, actually, in this strategy, we call it the synergetic optimization. We changing the slot die coating temperature, and we doing the substrate temperature control, and we can using the zero grade substrate. And finally, we can extend this strategy from the small area rigid device to the large area flexible device. This is the real image of our device. The reason behind that, actually, the morphology for the spin coating and slot die coating is quite different, because spin coating is a really fast drying process. But for slot die coating, all the solution is there. Their process is quite low. Drying process is quite low. Therefore, we need to increase the substrate temperature. And finally, we can get a similar morphology using the slot die coating of the 60 and 80 degrees. Their morphology are quite similar with spin coating as the room temperature. Their molecular arrangement on substrate are like vertical aligned on substrate. In this direction, they have better charge transport pathway. Yeah, this is the performance we can show you. Yeah, if the temperature is not well controlled, the efficiency is quite low. But with the high temperature substrate control, we can get repeat the high efficiency using spin coating technology. Yeah, these kind of solar cells, because they are very thin layer, they are really showing high flexibility after bending different type kind of the bending radius, bending, for example, 1,000 times, yeah, in the radius of 10 millimeter. Actually, you can see the PC is really stable. And also the shelf time of stability is quite good. If you put the solar cells there, actually, if you're doing testing their performance is quite stable. Yeah, but yeah, so we further actually increase the stability in the future by encapsulation or by interface modification. We want to further improve their light stability. This is modules we can show in your lab. Yeah. Anyway. I continue. Yeah. Anyway, we can making these modules with high we can making these modules and showing they can working as to charge the cell phones in the light, and also working as the power to power different kind of electronic devices. Therefore, just make a summary. Actually, we starting for the nanostructure, especially for the organic nanostructure control. We are making the flexible energy storage device. We can also making the flexible organic solar cells. And in the future, these two technology can work together to get the flexible energy storage, flexible energy system. With this, I need to thank my group and also thank my collaborators and also the financial support. Thank you for your attention.
Professor Wu, you are muted. You are still muted. We cannot hear you. You're still muted, Professor Wu.
Oh, sorry. Now we have 5 minutes for question and comments. So is anybody have some questions?
I actually have. Hi.
Yeah.
Very interesting talk. So when you mentioned, I'm asking about flexibility. So for example, you showed in the last part that you are bending 10 millimeter bending radius. So is this based on the, it's based on the silver grid? And is there also a transparent conducting oxide in these devices?
Yeah, actually, yeah, the structure of, can you see my screen?
Yes. Yes.
Yeah. Okay. Yeah. This kind of, yeah, we use the active layer is this composite, this kind of the blends, and the conducting layer is this kind of silver grade, and yeah, on the top of silver grade, actually we deposit P.PSS as interfacial layers, and after that we slot coating of this active layer. And finally, we actually not printing it, actually evaporate some aluminum electrode finally. And then we're doing the encapsulation. Yeah.
Okay, I see. So you skip the transparent conducting oxide this way.
Yeah, yeah. We don't use the ITO or zinc oxide.
Mm-hmm.
Thanks.
And perhaps I will also add a question. Thank you very much for the very nice talk. I'm wondering about the battery stability, if you can comment on the battery stability. And also, is there like a need for specific air-free or barriers in that sense of air or oxygen or humidity and so on for the flexible battery?
Yeah, yeah. You mean the flexible organic solar cells or battery?
Battery. I'm talking about the battery. The first part where you talked about the battery.
Part.
I'm wondering about stability and need for particular encapsulation, or is it just nothing specific? Or
yeah, for these flexible batteries, there's nothing specific, because actually normally we use the aluminum foil. It called plastic aluminum as the encapsulation layers. This can really isolate the water and oxygen out. Yeah, but to keep this flexibility, actually we ask our partners to provide some thin layers of the encapsulation layers, normally thinner than the commercially used aluminum foil or aluminum plastic. Yeah.
Thank you very much.
You're welcome. Yeah.
So I see we don't have further questions. So I hand it to Professor Markovich for the next speaker.
Okay, thank you.
Mm-hmm.
Yeah, thank you, Professor Wu. Thank you, everybody.
Thank you. So I would like to briefly introduce Professor Avner Rothschild, who is our next speaker. So Avner is a professor at the Department of, at the Faculty of Material Science and Engineering in the Technion, Israel Institute of Technology. He heads the group on electrochemical materials and devices. So he works a lot on electrochemistry and photoelectrochemistry, in particular for water splitting. And I would just mention, he had many achievements, and I would just mention his last award that he received last year, a very prestigious award on called the Eric and Sheila Sampson Prime Minister Prize for Global Innovation in Smart Mobility and Alternative Fuels for Transportation. And Avner, without further words, so the floor is yours.
Okay, great. So thank you very much, Gil. Hi, everyone. I'd like first to thank also the organizer for the opportunity to speak in this webinar. And let's get to the slides. Second, for some reason, I don't see them. Okay. So I'm going to talk about our research in the last 10 years or so about decoupled water splitting for green hydrogen production. And first, few words about green hydrogen. So green hydrogen is hydrogen that is produced by water splitting, also known as electrolysis. That's the reaction that is shown here, is simply breaking the bond between oxygen and hydrogen atoms in the water molecules. And the idea is that if you use renewable power, so electricity that comes from renewable sources such as wind or PV or others, then the entire process is called green because there is no discharge of CO2 to the environment. The uses of this green hydrogen are enormous, and this is a major component in our renewable energy landscape. It's not only for transportation, although transportation is obviously important, especially for heavy-duty transportation such as trucks, trains, etc. But it also can be used as a medium for storing excess solar and wind energy for use at night or for seasonal storage. And there's also a lot of important application for green hydrogen in various industrial applications, such as for producing ammonia, for the fertilizer, for producing metals, in the petrochemical refineries. So there are a lot of possible applications. The issue is that today producing hydrogen by this means, so by electrolysis that is coupled to renewable energy, is too expensive. It's at least 3 times more expensive than producing hydrogen by a process called steam metal reforming, so producing hydrogen from methane, and that's a process that emits CO2, which obviously we don't want. So the challenge is how can you make it better, and by better I mean cheaper. So in order to understand kind of the introduction to the topic, we need to understand the basics. And for that, I show you the principle of water electrolysis. So here in the picture on the left, you see a cartoon, a cross-section cartoon of a single cell. And these cells are stacked into a system that is called the electrolyzer. And the essence of the cell is 2 electrodes, the anode and the cathode, that are doing these electrochemical reactions of water oxidation and water reduction. So the overall is the water splitting reaction. And these 2 reactions are done, they are coupled, okay? So the hydrogen evolution reaction at the cathode and the oxygen evolution reaction at the anode, they are coupled in the sense that they are carried out at the same time at the same place. This introduces a major challenge that you have to separate these gases, otherwise you can have a mixture of hydrogen and oxygen, which obviously you want to prevent. So for this, you must have some separator, a membrane or a diaphragm that separate the cell into 2 half cells. And this introduces many challenges of sealing that make the construction of these devices quite expensive. So that is one major issue that we have. The other issue is efficiency. So this reaction, especially the anodic reaction, the oxygen evolution reaction, is quite expensive in the sense that there is a high energy loss that reduces your energy efficiency, and state-of-the-art electrolyzer operate at efficiency of less than 80%, which means that your electricity bill is more than 20 times more expensive than for an ideal process. And since the electricity bill is quite high here, is more than half of the production cost, obviously there is a big issue in reducing the loss and achieving near theoretical efficiency. So these are the main issues with conventional electrolysis. And our approach to solve them is by decoupling these 2 reactions. So by decoupling, I mean they are done either at different places or at different times. And I'll walk you through the different approaches that we have been working on in the last 10 years. So the first approach relates to a relative of a member of the family of water splitting, and that's photoelectrochemical water splitting. So instead of having 2 separate systems, one is a photovoltaic device that absorbs the sunlight and generate electricity, and then connecting the electricity to an electrochemical device that split the water molecule, the idea of photoelectrochemical water splitting is let's combine these 2 functions of light harvesting and electrochemical water splitting into one device. And the idea is shown schematically here. So that's the conceptual diagram of a photoelectrochemical cell with these 2 electrodes, the anode and the cathode. But here we make one of the electrodes, in this case, the anode, we make it photoactive. And that requires that this material here would be a semiconductor device. The semiconductor device has to be stable in electrolyte solutions. So this reduces the number of choices, material choices, and basically most of the material that survive this environment are semiconducting metal oxides such as titania, iron oxide, etc. If you look more closely at what really happens here, is here you have kind of an energy diagram with the conduction band and the valence band, and you see here photon absorb, excite an electron from the valence band to the conduction band. The holes diffuse to the surface where they react with water to generate oxygen atoms, and then the electrons go by the external circuit to the cathode where they generate hydrogen. So that is the concept. And for the last more than 10 years, I've been working on a specific material, is a form of iron oxide called hematite. That's the chemical composition that is apparently suitable in many senses. It is stable in alkaline solution, it absorbs visible light, and it is a cheap material that is also photoactive for water photooxidation. The issue with this material, the main issue, at least that's what we thought until not so long ago, is that the electron and hole, they recombine very fast in this material. So there is a very short length where you can separate and collect them before they recombine. This requires nanostructures, nanostructure devices in order to reduce the recombination. And our approach to this problem was by using ultra-thin films. And when I say ultra-thin films, it's films on the order of 20 nanometers. That's the distance where you can still have high efficiency of electron-hole separation without recombination. As you can see in the normal design, where you put these layers on a transparent substrate, you can see that they absorb very little light, okay? And the way to enhance the light absorption is by making a resonant device. So instead of putting on a transparent substrate, we put them on a back reflector made of silver-coated substrate. And then you can have, by resonance effect, you can have resonance that in the case of silver, kind of concentrate the light very close to the surface within 10 or 20 nanometers from the surface. And by that, you can absorb a lot of light and minimize the recombination. So based on this concept, we've been working for nearly 10 years, and still we could not achieve the expected efficiency. So the ultimate limit for hematite would give you 12.6 milliamps per centimeter square under normal sunlight radiation, but we can only get about 4. And no matter what we did, by improving the crystal structure, by adding different layers, selective layers, there is something like a glass ceiling that we couldn't break. So it took us a while, and then we realized that there must be another factor that, that will work here against us. And we started questioning what this factor is. And then looking at old literature on hematite that shows multiple electronic state, defect states within the bandgap of this material, we realized that maybe some of the photons that we absorb simply do not generate electrons and holes. They give rise only to local electronic transitions that cannot contribute to the photocurrent. So with that, we investigated and developed a method to actually measure this effect. We call it the photogeneration yield, and its wavelength dependence is called the spectrum. So essentially how we can extract this factor, which basically tells you how much of the total absorbed light actually contribute to electron hole generation. And we recently published, it was published about 2 weeks ago, an article that shows 2 methods for extracting this material property. And it shows you that about 40% of the photons are lost. And that's explained why we cannot get the 12.6 milliamps, but only less than half of the theoretical limit for this material. So with this, we learned that all photons are equal, but some photons are equal less than others. So let's step from the material aspect to the device aspect, or more so to the system aspect. So as you know, solar plants are comprised of many individual cells. Typically, the size of the individual cell is about 10 by 10 centimeters squared. So if you think about photovoltaic solar fields, it's not an issue, because even if you have millions of cells, it's easy to collect the electricity bimetallic line. By aluminum lines, you can collect the electricity from one cell to another cell, etc. It's not an issue. But in the photoelectrochemical cells, they generate hydrogen, not electricity, which means you would have to collect hydrogen gas from millions of cells. And this gas collection is a major issue. Here I can give you just a rough idea. So a small field that would generate 400 kilograms of hydrogen per day would require 3 million of these cells, which means at least 3 million of these tube connectors, 3 million of these T connectors. So just the gas piping system gives you a ridiculous cost. So we thought out an idea how we can eliminate this gas piping system. And based on the idea that our hematite devices, they generate only, the photoelectrochemical cell generate only oxygen. The hydrogen is produced at the counter electrode. And if we can find a way to move away these counter electrodes and concentrate them, let's say at the edge of the field, then basically we can eliminate all this gas piping issue. And eventually we find a solution how to do this. So if this is a scheme of the conventional electrolyzer cell, which is similar in concept to the photoelectrochemical cell, then we find a way to split these two half cells into two individual cells. And by doing so, we have to take care of the ionic transport, so the hydroxide ion transport between the cathode and the anode. They must go from, there must be a connection, an ionic connection between them. And the way we solve this is by introducing, in addition to the anode and the cathode, an additional set of two electrodes. We call them auxiliary electrodes, which are made of this nickel hydroxide, oxyhydroxide redox couple that is used in nickel metal hydride and other rechargeable alkaline batteries. And the idea is that one of these electrodes is charged in the hydrogen cell that produces hydrogen. The other one discharged in the oxygen cell that produces oxygen. And once they reach the full capacity, you simply swap them. So, and this enables you separation of these two half cells into two individual cells that can be separated over meters. So just to show the concept, here is the hydrogen cell at work. Here you have the hydrogen evolution at the cathode, and here is the auxiliary electrode that is just being charged. So transfer from nickel hydroxide to nickel oxyhydroxide. And then you can see the separated oxygen cell that does the opposite reaction. Okay, so with this concept, we were able to demonstrate a fully functional system of a photoelectrochemical cell that produces only oxygen, that is connected to an electrochemical cell that generate only hydrogen. And we tested it over with natural sunlight over the day, and you can see its reaction here. So this is one concept. There is still a challenge of the swapping, but working on this concept, we discovered something very interesting. So Avigail, my PhD student that was working on this concept, she noticed that if she leave the charged electrodes over the weekend and she come back on Sunday, she discovered that the charged electrode lost some of its charge. And then we check why this happens. And we discovered that this is simply the well-known phenomena in batteries that is called self-discharge, which is basically this reaction. A charged nickel oxyhydroxide electrode can react spontaneously with water and get discharged or regenerated while emitting oxygen. So in principle, this can save us the swapping of the electrodes. What we also discovered that this reaction can be enhanced by at high temperature, which give us a handle to control the oxygen evolution reaction. And with these notions, we come up with the idea of decoupled water splitting in a two-step cycle, where one step, the hydrogen generation, is carried out at ambient temperature, where you have the hydrogen evolution at the cathode like in normal electrolyzer, but the anode is now this nickel hydroxide oxyhydroxide system that is simply being charged, and you stop the process when it gets to full charge. Then you change the electrolyte in the cell from cold electrolyte to hot electrolyte, and the hot electrolyte induces this spontaneous reaction with water that emits oxygen, complete the water splitting cycle, and regenerate the electrode back to its original state, and then you can cycle this again and again and again. This concept, which we call ETAC water splitting, ETAC stands for electrochemical, thermally activated chemical reaction has two main advantages. One, it is there are no membranes, so this is a membraneless architecture, and also we achieve a high energy efficiency by this process. So just to show how we did this in the lab. So here you have the cathode, that a simple platinum coil that generate hydrogen. This is the anode that is being charged. Now it is moved to the hot electrolyte cell, and it simply emits oxygen by spontaneous reaction with the electrolyte, with water. So obviously, this is not the way we're going to do it in an industrial process. In an industrial process, we have multiple cells, and each and every one of these cells go through this cycle that is shown here. First, at low temperature, we connect it to a power source, and then we have hydrogen evolution at the cathode while the anode is being charged. Then we introduce an intermediate temperature electrolyte simply to wash the cells, to wash the remaining of the hydrogen from the cell. And then we introduce the high temperature electrolyte that induces this spontaneous oxygen reaction, and so on and so forth. So the advantages, as I mentioned, membraneless architecture and high efficiency. Disadvantages, this is the operation is a little bit more complicated because now it is not a continuous process, but a batch process. And the temperature swing between the cold and hot states requires some thermal management. Overall, we achieved extremely high efficiency for this reaction, close to the theoretical efficiency. So specifically, we operate the cell at current density of 50 milliamps per centimeter square at an average voltage of 1.5 volt. Obviously, the voltage and the anode potential changes during the reaction because the state of charge changes, okay? But the average is very low, is 1.5 volt compared to a state-of-the-art electrolyzer that operate at 1.8 volt. So we can save more than 20% in the energy. This reaction is highly cyclable. So here you see 100 cycles, except for the first 10 cycles where the state of charge of the electrode changes. Once it reaches the operation range, then all the remaining charging curves repeat themselves exactly. And if you look here, so for 100 cycles, the average potential stays exactly the same. We can also increase the current density with a small payment in the operation voltage. The reason why this reaction is so efficient is explained here. So first, let's look at the conventional OER. The conventional oxygen evolution reaction involves 4 proton-coupled electron transfer steps. So it's a 4 electron per 1 site reaction, okay? And in order to have no overpotential, you must have that each and every one of these 4 steps has exactly the same barrier, energy barrier, as all the other steps. But this is not what happens. In reality, different steps have different energy barriers, and specifically, it was found by looking at many different electrocatalyst compositions that the barrier between the first intermediate and the third intermediate, instead of being 2.46 electron volt, is 3.2 electron volt. So it means that we have a minimum overpotential of 400 millivolts, and that is before the reaction occurs. That is at 0 rate. So that is called the minimum onset overpotential, which for the oxygen evolution reaction, because it's a 4 electron reaction, basically you have a huge loss of efficiency here. By replacing this oxygen evolution reaction by the charging reaction of the electrode, we go from 4 electron per 1 site to 4 1 electron per 1 site charging reaction. So basically we charge 4 nickel atoms, and then we release the oxygen from all 4 of them. The release of the oxygen is done without applying current. So therefore, the only potential that we spend is in charging reaction, and that's a 1 electron reaction that has no minimum overpotential like the OER. Here you can see that, if you look at the regeneration reaction that occurs spontaneously, conceptually, you can split it into an anodic and cathodic reaction that occur spontaneously at the same electrode in different regions. And then you see that these two reactions are simply the discharge reaction and the oxygen evolution reaction. And the electromotive force, or the potential difference between the two of them, gives you an electromotive force of nearly 200 millivolts, which is the reason why this reaction is spontaneous. So here you can see this on the cyclic voltammetry diagram that show you the charging and the discharging reaction and the oxygen evolution reaction. And here you can see the distance between the oxygen evolution and the charging reaction is basically what gives you the gain in the operation voltage. And also, if you look at the charging curve, you see that once we fully charge the electrode, it starts to generate oxygen, which obviously is something we don't want. So we stop when we see this potential plateau. We verified with dissolved oxygen measurement that as soon as the potential starts to plateau, that's the point where oxygen starts to evolve, where below this point there is no oxygen evolution. So this gives us an easy handle when to stop the cycle. So a few words about this material, this nickel hydroxide material. First, I already mentioned it is used in alkaline batteries. Specifically, it is used also in nickel hydrogen batteries that are the most robust batteries that are known, and that's the reason why they're used in space missions such as the Hubble telescope, where they can survive tens of thousands of cycles, which is obviously very important. For the survival of these electrodes, it's very important that we cycle them only between the beta-beta phases. So in the nickel hydroxide system, there are 4 phases. 2 of them, the cycling between them is cyclable. That's the beta nickel hydroxide, beta nickel oxyhydroxide. We don't want to reach the alpha and gamma phases because the interlamellar spacing between them changes upon cycling. So we limit ourselves to the beta-beta cycle, and the way to do this is by monitoring the potential as I showed before. And if you look at what really happens here, this is the crystal structure of the nickel oxyhydroxide system. So you have nickel O2 octahedra with equatorial hydrogen on its oxygen. On the other phase, on the charge phase, you have equatorial hydrogen only on every other oxygen. So basically the discharging reaction occurs by diffusing of protons in and out of the lattice, where eventually the proton reacts with hydroxide ion to generate water at the surface. So obviously the charging and the discharging reaction is limited by solid state proton diffusion with these layers, which is why making nanostructured material is very important. So the way we do this is by electrodeposition on nickel foil, so a highly porous substrate, nickel foil. I'm sorry, not nickel foil, nickel foam substrate. And here you have the large pores come from the nickel foam. These are nearly 0.5 micron voids. But what's important here is the active layer. The active layer is about 10 micron thick of the electrodeposited nickel hydroxide. We also dope it with cobalt to improve the performance. And the structure of this layer looks like a coral. So it is basically a nanoflake morphology with very thin flakes. The wall thickness here is about 20 nanometers, which gives you, first of all, the overall thickness is high, is 10 micron, which allow you a lot of active material. So this gives you the capacity. And the short distance for the solid state diffusion that comes from the thin walls give you the high rate performance. And this would enable us to charge these electrodes at high current density, as high as 200 milliamps per centimeter square. That's very high compared to battery electrodes, multiple times, and still keeping high capacity, which obviously both of them are very important for our application. So we started with nickel foam electrodes. Now we do this on carbon cloths that give us the flexibility and the potential to reduce the fabrication cost. We noted that on the carbon cloths, because of the flexibility, we get much less drying cracks, which means that the adhesion is much higher. And currently we explore this opportunity of working with carbon cloths. So in the lab, we generate these tiny electrodes. So 2 by 1 centimeter Obviously, for production, we must scale up the production, and that's done at the company H2 Pro that we established about 2 years ago, that is now building an industrial scale electrodeposition line that looks like this, and is building systems that look like this. The company is basically commercializing this technology. A few months ago, it raised $22 million from very famous people such as Bill Gates and Li Ka-shing. We also won past year the New Energy Challenge of Shell. So the commercializing of the technology is done here at the company. And I think I reached the end of the talk and time for questions.
Thank you very much for this interesting talk. I want to mention, I see people didn't write any questions in the Q&A, so I would like to encourage people to do that and write questions.
Thank you very much, Avner. This was really fascinating indeed. I also encourage also questions from the audience. But I'd like to ask, is there the prospect of, let's say, combining the solar part with this newest technology that you introduced now? I mean, the newest technology that you have the company with is the thermal cycling idea. And is there a prospect of going with solar to H2 in your mind for commercial application in some way?
Yeah, I believe yes, Uri. So if you kind of how I build this this lecture is, I told you the history where we started. We started by thinking of a way that will solve the issue of collecting hydrogen from millions of cells. Okay, so that's how we started to work with this nickel hydroxide oxyhydroxide as a charge storage electrode. And then we tackled the problem that we had to swap them. So mechanically swap them, yes, the auxiliary electrodes. So we had two separated cells with two auxiliary electrodes that are being charged and discharged. Once they reach the full capacity, we had to mechanically swap them. And that's obviously a big challenge or a big operational challenge, yes? And then we thought about multiple ways or possible ways of how we can do something else instead of the swapping. And that's actually how we came to this thermal cycling. So perhaps if you come back to this and now you combine this ETAC process with a photoelectrochemical cell, and now instead of swapping the electrode, you simply find a way to heat the cell, but you need to heat it to, I can tell you, above 60 degrees, okay? Above 60 degrees Celsius, you get this reaction starting to happen at a reasonable rate. And the higher, the better. So we operate this, the TAC stage at close to boiling temperature. So if you can find a way to run hot water in the photoelectrochemical cell, then yes, maybe this will solve you the issue of swapping somehow.
Okay, in the meantime, there is a question from the audience for you about kind of cost estimate for H2 per kilo with this technique. What are the prospects for this and what is it now and so on?
Okay, what we say is dollar per kilogram. How we get there, we do not know.
Okay. And Professor Wei, I see you also have a question.
Yes, thank you, Professor Rashid. Really nice presentation. I enjoyed that. Yeah, my question is about the EQE or the photochemical cells. Normally the EQE is quite low, lower than maybe 40%, something like that. Yeah, what's the theoretical limitation of the EQE for photochemical cells? And also how can really improve this kind of EQE in photochemical cells? Yeah.
Okay, so EQE of different, is not the photochemical cell, it's actually the material, okay? It's the photoelectrode.
Yeah. Yeah.
So for some electrodes, specifically for titanium oxide, the EQE is, is near unity, okay? So let's say 80%.
Okay, yeah.
Similar to high efficiency photovoltaic solar cells.
Yeah,
also
but once this wavelength extend to the visible range, normally the EQE will decrease, right? Yeah.
Well, the issue, no, the EQ is still high. The problem is, with titanium, the problem is the band gap energy. There is no light absorption in the visible range. It only absorbs in the UV range. So that's the issue. I mean, the EQE is high in the region of absorption, but the problem is the region of absorption is too small. That's also true to bismuth vanadate. Bismuth vanadate is also very impressive research over the last decades improved the quantum efficiency of this photoelectrode material that is now close to 90% over the absorption rate. But also for this material, the band gap energy is too high. If I remember correctly, it's 2.4, 2.5 electron volt, which is still too high. Hematite has band gap energy of near 2 electron volt, which means that this is already meet the criteria. So in principle, if you have EQE of 100% across the absorption rate, you can potentially expect to have 12.6 milliamps. But now there are two issues. One is recombination that kills the EQE, but recombinations you can fight by nanostructuring, okay? And many people, including ourselves, have been fighting this recombination challenge for many years with limited success. So we have made progress, but still we stuck, okay? Nobody, as far as I know, was able to reach more than 5 or 6 milliamps with this material. That is less than half of the theoretical limit. So that led us to believe that there must be something else beyond recombination. And this something else is what I explained, and you're welcome to read this article where we have more details. It comes from a localized transition. So many of the photons we absorb, about half or even more than half of the photons that are absorbed in hematite, they excite localized transitions. So it's not an electron moving from valence band to conduction band, yes, and give you extended state. No, it's a localized transition. It's simply from one d orbital on an iron atom to another d orbital on the same iron atom. So the photon is absorbed, but there is no mobile charge generation. So this basically kills about half of the photons.
Okay, great. Thank you.
Thank you.
Okay, Professor Wu, it's your turn. Yeah, you are muted. Professor Wu, you are muted.
So now we go to today's third speaker, Professor Yin Hongfeng from Ningbo Institute of Materials Technology and Engineering, CAS. Professor Yin's research interest is focused on construction of nano-sized metal oxide and cool shell materials with confinement structures and their catalysis applications in organic molecule conversion. He received his bachelor degree in 1999 from Nanjing University and PhD degree in 2006 from the Ohio State University. Then he carried out postdoctoral research at the Oak Ridge National Lab in USA. In 2010, he joined the Ningbo Institute of Materials Technology and Engineering as a professor. Professor Yin has published more than 50 papers and applied more than 30 patents. So now we welcome Professor Yin for his talk.
Thank you, Professor Wu, and thank you, organizers. And it's my pleasure to meet all the professors here on web, and very glad to have this chance to share my work with colleagues. Okay. Okay, can you see? This is my work. My topic is design and synthesis of nanomaterials with cold shell and strong metal support interactions for catalysis. You can see on the front page, this picture is our institute. It's big and a pretty new institute. And currently, you have 2,500 grad students and professors. This is the outline, and my focus will be the coaxial nanoparticles with confinement effect. So the nanoparticles and the nanomaterials have broad applications because these properties, small size effect, surface effect, and so on. It can be used as devices, it can be used in medical, and it can be used as catalysis. And in the catalysis, it used its small size effect and the surface effect. Because for all the catalysis reaction, its size is around nano size, but it also takes advantage from its small size. We want the reaction to happen. We want the catalyst to be particle size to be small because it will very high surface energy. We also want it to be very stable so that the catalyst can be used for a long time. But the catalyst also suffer from its small size and pretty big surface, because when the surface is big, that means the high surface energy, and it means it will prefer to aggregate to lower its surface energy and become pretty big to aggregate. So it also suffer from its surface high surface energy. So here comes to the question: can we prepare to get the good a good catalyst with both high surface area and good activity, as well as very stable status? So here comes the question. That's the challenge. Can we have an active, selective core as well as well-controlled size as catalyst? To solve the problem, we have proposed to do this. We prefer to form the strong metal supporting reaction through metal oxide. For example, if you put the gold on iridium oxide, the gold iridium have very strong metal oxide interaction. Then the gold itself will be bind to the iridium oxide, and when there's a high temperature, the gold will not aggregate because it's being controlled by the iridium oxide. So by forming the strong metal supporting interaction, it can be a way. Another way is that making protective oxide coating in form of cold shell structure. For example, we have a pretty small gold nanoparticles, and we coat it with pretty stubborn silica or zirconia shell. When then it will form a cage to prevent the gold nanoparticle from aggregate at a high temperature. That's a pretty good way. So by constructing the shell, it can change the property and function of original nanoparticle. That will lead to new performance of the particle to kinetic activity. Also, it can improve the thermal stability, as I just mentioned. So by combining these two, like form strong metal supporting interaction and make a cold shell structure, that's the target we are trying to do. For example, this is a cold shell structure. We have a normal metal nanoparticle as a core, and we have a metal oxide as support and promoter. Metal oxide have a pretty good interaction with the normal metal, and it also can be work as a promoter. Then this structure has a shell with a mesopole. The shell can protect the normal metal from aggregation. With a mesopole, that will not will allow the substrate to transfer in and the product out. So it will be a pretty good way to solve the aggregation problem as well as to have a good activity. There are many work have been done to do this way. For example, the silica gold as this can have a interaction as well as a carbon as a shell. Another work like gold have good interaction with iron oxide, and the shell can protect it from aggregation. So noble metal oxide co-shell structure, it can improve the anti-sintering property as well as make the catalytic activity from nanoparticle. That's the target. I'm going to talk about my work. This is one pot synthesis of gold iron oxide in silica. That's the silica is a shell. For example, we use the surfactant and the gold precursor and iron precursor. By reverse Michel reaction, it will form this gold iron oxide with a silica shell nano reactor. Well, I'll talk about the structure later. Well, we can change the ratio between the gold precursor and the iron precursor. So we will have a different nanoparticle, element ratio of this nanoparticle. This is the XRD of the particle we have made. We can say that with gold only, this is a peak pretty sharp, and with introduction of iron, then it will become not so sharp. So, and also from the XRD, we cannot observe only iron gold alloy peak or only iron oxide peak. So introduction of iron does not alloy with gold. Well, with forming the gold iron oxide and the composite, this gold crystallinity will be reduced. Okay, this is the TEM of all those nanoparticles we have made. We can see by introducing, no matter how much of the iron we have introduced, we can all form those good shape of the gold nanoparticle and gold iron oxide nanoparticle with the silica and shell. So this co-shell structure is pretty clear. This is the particle size of the different nanoparticles. We can see by different with different gold iron ratio, the particle size differed from 3.2 nanometers to 3.5 nanometers. There's no big difference. This is a mapping of the elements. You can see that gold and iron are mapping. They are at the same position. So that indicates that the gold and iron have a very good close contact. This is a DT result. We can see that with an introducing of iron, the bead surface area increased from 130 to 316, while the pore size didn't change much, and total volume also introduced. So this is because of the influence of the iron hydroxide co-precipitation on the condensation process. That will make a pretty big pore volume. This yield this, we can see that even though there's no iron gold alloy form, the formation of iron oxide gold in composite will still make the red shift of this gold peak. So it will also make the gold electrons become insufficient. Well, this is the FTIR. We can see that with when there's no iron introduced, we have a linear type and the bridge type of carbon oxide. But with introducing of iron, the two peaks will merge, and finally will become one peak. So that means more iron introduced, the gold surface will be covered. So the exposure of gold surface will be pretty low. And here come to the when we use it as a catalyst, we can see that. It doesn't mean that we introduce more iron, the catalytic ability will be good. We can see for when there's no iron, there's almost no catalytic ability. While with introducing of iron, the catalyst ability will increase. While it will reach the peak when the ratio of gold ratio of gold iron is 1:2. With more iron introduced, the activity will reduce. Well, when we pick up the ratio of gold to iron is 1:2, the catalytic activity is pretty stable. We can see that at 270 degrees Celsius in 40 hours, there's no degradation. So that's what we see for the iron and gold with silicon as the shell nanoparticles. Here we come to the iron, gold iron nanoparticle with zirconia as the shell. If we replace the shell by zirconia, this synthesis is in step, not the one-part synthesis. We first synthesize the gold iron nanocomposite, and then by introducing the silica precursor, we form this structure, and then we introduce a zirconia precursor. So it will form a zirconia shell on surface. Then by etching, we remove the silica. Then we finally have this gold, iron, core, and the zirconia and the shell nanoreactor. This is the picture, TEM picture of all the structures. So the first picture is the gold iron oxide nanoparticle. You can see it's pretty good. And by coating the silica, it forms a very uniform and union dispersed structure. And by coating the zirconia, we can see the staggered zirconia on the surface. And by removing silica, we will see pretty good structure of this. We can see the zirconia outside and the very good gold iron oxide particle clearly here. So that's what we think. And the particle size didn't change much during the synthesis. And for the mapping, we can see clearly all those kind of distribution of elements, and the distribution of gold and iron are at the same position. That means the gold iron has a pretty good contact with each other. And this is the UV base. We can still see that because of interaction between gold and iron oxide, so that's the red shift. And for the catalysis, when there's only iron, there's almost it has very bad catalytic ability. Well, when there's only gold and iron oxide or zirconia, without this kind of coshell structure, the catalytic ability is as this. With introducing our target coshell structure, you can see that catalytic ability increased a lot. And we also did this this reaction a couple of times. You can see that there's also almost no change. That means this structure is pretty stable. And we run a long time reaction. I mean, there's almost no change. And then here is a pretty good result. We know, as I mentioned, this nanoparticles are pretty easy to aggregate, especially for the nanocatalyst. But for this structure, we calculate at 900 degrees Celsius and did the catalysis. Again, we can see that all this light-off curve matched pretty good with the original one. That means it's a structure not changed. So it has very, very good, outstanding thermal stability. This is the TEM of the nanoparticles First is that just did the reaction, and the second is that after calcination at 900 degrees Celsius, you can say there's almost no difference. So that means it's very sinter resistant. So this structure is very stable and very good. We can also change the coal from the iron, gold iron oxide into iridium cobalt oxide. This is the synthesis step, as I mentioned here. Is no, it can be made from iron cobalt to form cobalt or iron iridium cobalt alloy, and then by calcination will form iridium cobalt oxide nanoparticle as a core, and the mesoporosilicon as a shell. And this is the structure we can see clearly a very good core shell structure. And for the nitrogen absorption desorption, we can see it has a very good mesoporous structure. As for the for its catalysis, we did it 10 times of hydrogenation of nitrobenzene reaction, and we did it 10 times. You can see that its conversion only reduced about 2%, and its selectivity reduced only also 2%. So it's a pretty stable and stubborn catalyst with this structure. The shell, we also did the work to change the shell from pure silica or zirconia into silica alumina complex. With the reverse micelle procedure, we can prepare this platinum cobalt nanoparticle with silica as shell, and by etching and by introducing alumina species, we can form this platinum cobalt oxide as core, and the silica alumina and shell nanoparticle. From TM, you can see it has very good shape, image, and XRD, and also the BET. Well, this structure has a pore size about around 4 nanometers and the space size around 40 nanometers. This is the mapping of this structure. For silica and alumina, we can see that these two elements are at the same position, means it is a uniform structure. And for the platinum and the cobalt are at the same position. That means it has a good interaction. Well, besides all the previous work we have done, we also did other metal as a core, or metal oxide as a core, and other metal oxide or oxide as the shells. For example, we use palladium or platinum nickel oxide as core, and mesoporic silica as shell, and nickel as core, zirconia as shell, or gold palladium or gold palladium alloy as core. So that's the work we have done. Next, I'm going to talk about some industrial application based on the work we have done. We did this. Based on our work, we developed the catalyst with magnesium oxide and tungsten oxide, and the catalyst to do the olefin metathesis. This work has been used for the industrial applications. And then we also developed catalysts to use syngas to produce ethylene glycol. First step is carbon catalyst. This is palladium alumina catalyst. You can see pretty good shape. And for the second step is a hydrogenation catalyst. This is a copper silica catalyst. These two catalysts have been industrialized and been used for the industrial production. So that's my work, and I would like to thank my postdoc, Hongbo Yu, PhD student Fan Yang, and master student Zhentong Guo, and then also thank my group. So thank you for your attention. I'd like to take any questions.
Thank Professor Yin for his excellent talk. Now we have 5 minutes for the questions and the comments. So maybe I ask one question. So nowadays, you know, the single atom catalysis is a very hot topic. So from your talk, you have used this strong metal support interaction. So does this kind of interaction can be extended to stabilize the single metal atoms than to realize the single metal catalysis at higher temperature?
Yes, the strong metal support interaction can be used to stabilize the metal to facilitate the formation of single atom structure, and it can be used in the single atom catalysis. But for the high temperature reaction, single atom catalysis is a problem, because the single atom must have a very strong interaction so that it will not aggregate or migrate during high temperature. But if the interaction is too strong, that means the single atom may not be so active for the catalysis. So that's a dilemma.
Okay, thank you.
And if I may add the question as well, Professor Yin, thank you for the interesting talk. You have this core shell concept with silica, and then you have a nanoreactor inside. Is there any insight? What is like an optimal pore size in this case? Because you need the reactants to come in, you need some, okay, you have some confinement, which is good for the catalysis, but then also the products must depart away. So is there some consideration of design that you can comment on pore size in these nanoreactors?
Yes, the pore size is a pretty big issue in this kind of structure. As you mentioned, we must let the substrate to come in and the product to go out. The pore size, we can control the pore size by using different surfactant. The surfactant with different chains. When the chain's length is different, the pore size will be different. So we can control it very easily.
Okay. If no further question and comments, we welcome first thank Professor Yin, then I hand it to the Professor Markovich for the fourth speaker.
Yeah. So thank you, Professor Yin, for the interesting talk. And we move to the last speaker of this session. This is Professor Lioz Etgar from the Hebrew University in Jerusalem. Lioz graduated from the Technion, and then he did his postdoc studies in the famous group of Michael Gratzel at EPFL, Switzerland, working on photoelectrochemistry. And since 2012, he's at the Institute of Chemistry at the Hebrew University of Jerusalem, and he focuses on various innovations regarding solar cells based on perovskite materials, and he has done very prolific work in this domain. And Lioz, the stage is yours.
Thank you very much. Thank you for the invitation to talk at this webinar. I will share my screen with the presentation. Okay. So I'm coming from the Hebrew University at the Institute of Chemistry. I will focus my presentation on the hybrid perovskite and its application in solar cells. One of the subjects that we are focusing in my lab. So I will try to focus the talk on those 4 topics related to solar cells and the development of the materials. So just since we didn't talk about perovskite in this webinar so far, so I want to show a little bit the motivation of working with perovskite, the people who are not familiar with this. So this is the NREL solar cell map, which gives all technologies and the efficiencies according to the year. But what really happened recently, and I will emphasize it, is that since 2012, the perovskite start to be used in the solar cells, mainly in the solid state devices, achieving today more than 25% in laboratory scale. And this is really a huge increase in the solar cell community. And this perovskite is really a hype in the field. And I want to go on several properties of this perovskite before going to the structure. So first, the main reason is that we can make it from solution, which makes it very easy to prepare. It has a broad absorption. You can make several device structure out of it, and I will show some of them today. You can make it on flexible substrate. You can control the optical properties very easily. And at least calculations shows today that it has some promising also in terms of cost, which also push this technology to some commercialization. So what is the structure? This is a hybrid material. You can also make it a complete inorganic, which means that it composed of a metal, usually a divalent metal. Could be lead, this is the most common one, but can be exchanged to other metals such as tin. It has an octahedral configuration, which means that it's surrounded by 8 halides, could be iodide, bromide, or chloride. And finally, it has a cage, an open space inside this perovskite, which a cation, which require an amine group, should be put inside. And here you can play a little bit with methylammonium, foramidinium, which fits into this size, or you can take an inorganic cation like the cesium, and then you make a full inorganic perovskite. As I said before, you can control the optical properties quite easily by the chemistry, which means that the halides are the most one who influence the optical properties, but also, and I will show today also the cations, the metals here can control optical properties, and also the A cation on this side. So I want to introduce what is in the last few years really getting some interesting in the perovskite community, and this is the low dimensional perovskite. What is the idea in the low dimensional? If we take the normal 3-dimensional perovskite, like I showed you in the previous slide, this is the structure. But what happened now if I put a cation instead of these yellow dots, which do not fit into this cage, then we can start and create layered materials. And we can control the number of layers by the stoichiometry of the small and the large cation. The easy part, because it's coming from solution, you can create a pure 2D material like N=1 here very easily, but because, and this is the disadvantage, because we are making it from solution, it's really hard to control once you are going to N=4 or 5 and more, how many layers you really have inside. Probably it's quite a mixing of several layers. The idea behind using low dimensional perovskite is when you are getting an organic cation, it has some hydrophobic chain, which gives some resistivity to humidity to the perovskite, and this is something we want to improve in terms of stability of this material. And following this, we started to think on a new cations that can improve the structure of the perovskite. From one side, improve stability. From the other side, make some organization of the layers on the substrate. And if so far, the most common cations were used just one ammonium group, as you can see here, it could be with benzene or any other carbon chain. We took a diamine group, and this diamine, the main difference is that it actually holds the inorganic framework by ionic bonding and not by van der Waals interaction. And this hopefully can make a much ordered structures than before and make the distance also between the inorganic framework shorter. And I will start from the results. So when we implement this into devices of resources, indeed, at very low end value, which means almost a two-dimensional material, we can create a nice devices more than 15% efficiency, which is quite amazing since so far when you reduce the dimensionality of the perovskite, you increase stability, but on the other hand, the conductivity through the layer is really bad. And in this case, you can see here nicely that it didn't harm the performance. And then we started to do some characterization, if it's Hall effect measurements, which can estimate the Hall mobility. And this is mainly more or less the Hall mobility of those perovskite around 1. It's much lower than the silicon on one side, but on the other hand, it's much higher than the organic materials. So it's really something in the middle, which still permits some good conductivity in those layers. We perform some charge extraction voltage decay, which can tell you about their combination rate in those kind of devices. And indeed, the low dimensional has a much lower combination rate compared to the three-dimensional perovskite devices. Finally, we can assume that this ionic bonding, since we have two diamine group, can form a much organized structure between the two electrodes, the anode and the cathode, compared to the case of monoammonium group, which then you have probably a mixing of layers. And this we can see nicely in the performance. I would like to mention that this work was done in collaboration with Professor Meng from the Chinese Academy of Science in Beijing, under one of the ISF China-Israel project. When we move to the stability of those cells, you can see nicely, this is a stability under cycles, which means that you are continuously illuminate your device, then you close the light for a few minutes, and then you open again and again, and you see nicely how the recovery in each cycle of the device, this is the low dimensional one, the pink one, but when you go to the three-dimensional, it starts with a nice recycling, but then it's going down and down in terms of stability. This is for under illumination, and if we check it under humidity, again, the three-dimensional decreased very fast, while the low dimensional still decreased, but much slower. Still needs to improve, but you see the difference. And this is devices even without encapsulation, which means that they are really in a full humidity outside, and still they are working. And this is a big improvement compared to what we had before. So this is some work on the low dimensional. And if I keep going and would like to show you some of materials development. So our next step was how we can take the all inorganic perovskite, which is based on cesium lead iodide, which is a very promising one because it's a fully inorganic on one side and absorb the whole visible range. But on the other hand, it's not stable under room temperature, which means that very easily it's go from his black phase, which is photovoltaic active, to something which is no photovoltaic active with a wide band gap, and you cannot use it. And there are several ways to try and stabilize this structure. And we thought on a way to create an alloy structure, which means that we can create some mixing of lead and tin at the metal site, as you can see here. If you look on the size of the cations, they are not on the same size, which you will see in a minute create some tension in the crystal. But on the other hand, this tin should stabilize it instead of the cesium lead iodide completely going to the orthorhombic phase, which is unstable and non-active, maybe this addition of tin will make some stabilization to the structure. If we look on the tolerance factor here on the bottom, tolerance factor tells us if this perovskite can really form. And indeed, if it's over 0.8, it can form, but this also tells us that this tolerance factor is not the accurate parameter to look. Actually, it was invented for oxide perovskite, and this is why it's not so accurate in this case. So the first observation was very nice to see that when you add tin to the lead, which means instead of the lead you add more and more tin, you can push the absorbance through the near IR. If usually perovskite absorb until, if it's all inorganic, until 700 or 800, you can go even to 950, which is something obvious, which is good for of course, for photovoltaic devices, as you can see here. So this was one nice observation to get. In terms of stability, indeed, when you put more and more tin, and this is the time until degradation of the film under continuous illumination. And you can see nicely when you put more and more tin, the films survive outside without degradation. And this is amazing because when you take cesium lead iodide, after 2 minutes, it's going to yellow. And here, while you add in some tin, you can get much stable structure to the device. So you get two benefits out of it. First, better stability. Second, much wider band gap. And this is two properties that you want. On the other hand, when we check some Hall effect measurements, you can see that when you put more and more tin, indeed, you have much higher Hall mobility, which means that the material become more and more p-type. And this is on the other, and this is actually something that it's not so good for us, since we want to get a much better conductivity as an N-type material. And in the same case, if the Hall mobility is going up, also the carrier concentration is going up when you put more and more tin. So as I said before, on one side, the tin helps you to stabilize the structure, gives you a wider band gap, but create your material more and more p-type, more and more Hall conductor instead of electron conductor. We did some UPS measurement, and this is with collaboration with Professor Anthony Kahn from Princeton University, which we measured all the energy level for the different combinations, as you can see here. So those are accurate value of the conduction and valence band. And what was very interesting to observe when we did some calculations, if the material can create orthorhombic structure or a cubic structure, this is the blue dots, you can get those kind of trend in terms of the addition of tin. And the experimental shows that the experimental is really standing between those two, which means that we are not exactly an orthorhombic on one side and not exactly a cubic on the other side. And this is because we have two radius of the lead and the tin in the structure. This actually predicts very nicely what we observe when we put more and more tin into the material. Finally, we introduce them into the devices, into solar cells, observe very nice performance, like more than 12% with 1 volt VOC. And this was something promising to observe with all inorganic perovskite, with let's say a reasonable stability, not something that degrades in 2 minutes. Here you can see the stability of those. This is a full device stability. As you can see, it has some degradation in the first few hours, but then it stays quite stable for a much longer time. The whole issue of 3-dimensional compared to 2-dimensional is something that very arising a lot of questions in the community. Recently, I published some perspective on this, which gives the idea or what can be done or what can replace the 3-dimensional instead of compared to the 2-dimensional perovskite, the one who are interesting to look at. Now I want to talk about two different device structure, also based perovskite. This is a Hall conductor free based on carbon as one of the electrodes, and the structure here is completely different. The first one is mesoscopic carbon perovskite cells. And the idea here is that you are creating a stack of several layers. The bottom one is mesoporous TiO2. The next one is mesoporous zirconium oxide. And then the last one is a carbon, also with some porosivity, a carbon layer, a very thick one, as you can see in the cross section. And finally, when you print all those layers by screen printing, you drop the perovskite from the top, and this penetrates the whole way down. So we developed a two-step deposition for this sorrow cell. The first one, we are dropping the first precursor, which usually is the lead iodide or the lead halide, and then we dip it in the second one. As you can see here, we did some EDS line scan after FIB cross-section in order to see that all elements penetrate the whole way, because we are talking about like 10 to 11 micron devices. This is not obvious that everything is penetrating. This proves that the penetration is really essential for the performance of the cell. We did the optimization in terms of the dipping time in order to get the best performance. We achieved like 15% efficiency. This is quite high for those kind of cells, one of the best today. As you can see here, we performed some also different active area for those devices to show that they are really not affected by the device area. And finally, we move to the stability. Since those carbon cells, let's say the main advantage coming from their stability due to the carbon layer on top, or that coat the device. If we start with the shelf life stability, you can see nicely that this is days, it's even not hours, that it's quite stable, still not the optimum, but we have to also to understand that we are talking about unencapsulated devices outside, and this is something nice. But when we move to more sophisticated stability measurement, and this have been done with collaboration with Professor Iris Visole-Fischer from Ben-Gurion University. And those measurements were done under continuous one sun illumination, holding at maximum power point. So you can see that they are degraded after, let's say, 180 minutes. But what was really interesting, when you are keeping them now, you stop the measurements, you're keeping them one day in the dark, and you start to measure again, they recover almost to the complete starting point. And this doesn't happen in other devices, and we wanted to understand the reason for that. We did some XRD measurements following those kind of steps, which means before the illumination, after 3 hours of illumination, after the recovery. And what we found that the unit cell, something is changing there during time. And what we are assuming is that happening is that finally, since all the precursors are sitting in those mesopores structure in a very close proximity, it degrades, the precursors are separated, that's mainly the lead iodide, the cation, and probably those two. But then they are sitting in the dark for a long time, and a reaction happens again between them and create, again, the perovskite. And this cannot happen in a normal device, since in a normal device you have a flat layer, and those precursors are not really in close proximity to have this kind of effect. And this is very nice to observe, and maybe could be also practical, since finally in the sources you have some night. So maybe in the night it can recover and work again good during the day. Recently, following the idea of the carbon cell, and this is something really new, we thought on making ITO-based cells, which means that instead of the carbon, we're replacing by mesoporous ITO electrodes that will function as a transparent electrodes and as a mesoporous electrodes, the same concept like in the carbon cells. What is the fabrication? Fabrication also here is based on a screen printing technique, as you can see here. So usually we are starting with an FTO glass, and then we start to print the layers. It's a mesoporous TiO2, mesoporous zirconium oxide, and then we print the mesoporous ITO, which we developed in the lab. and we drop the perovskite. So this cell can be done in few hours, ready, very easily and very, very stable. Here is the cross-section of the different layers. And here again, also here we did some EDS line scan. So this device gives today an average of 15% efficiency, quite impressive for those newly developed devices. Stability is amazing since we are not dropping at all the performance for the whole parameters. And what an additional properties that we found out, that we can recycle the perovskite inside, which means the scaffold of these mesoporous metal oxide materials are very, very stable, which means that you can wash the perovskite and then you implement a new perovskite and it's working almost the same like before. As you can see here, those are, for example, 3 cycles made from the fresh one, and then we wash, we dip it again, then we wash, we dip it again, and you see nicely how it works, which means that if you have some degradation of the material, this scaffold can work again and again as a full device. As I said before, since we are using ITO, it has some transparency, and one of the motivation was that it can be used later on for a tandem structure. And here you can see, for example, a demonstration of different halide percentage in order to show you the transparency of the electrodes. For example, in the carbon cells, this cannot be done due to the complete dark of the carbon. By that, I want to finish. So this is the summary. I present you the low-dimensional perovskite, a new concept using diamine, the opportunity to go to the near IR is the perovskite by using lead and tin, and not necessarily that the tin is harming the stability, is doing the opposite. And finally, a 2 new structure in terms of mesoscopic carbon cells and the ITOs that we recently developed. I want to thank my group and the few collaborators, as I mentioned during my talk. If it's Anthony Kahn, who helped with the UPS measurement, Professor Meng, mainly with the low-dimensional perovskite, and Professor Fisher with the stability measurements. And thank you for your attention. Thank you.
Thanks, Lior. Thank you very much. So let's see if there are questions.
No questions from the audience right now.
Someone raise hand. I don't know.
Yeah,
what does it mean?
Professor Wei.
Hello. Yeah. Nice talk. Yeah. Actually, I have several questions. The first one is in your first case. Actually, the stability, the efficiency decreased and then recovered after some time. Yeah. What's the mechanism behind that? This is the first question. The second question, actually, 2-dimensional perovskite material is quite popular, and because it can making some material and device with high stability. But I want to know, but the efficiency normally lower than 3-dimensional, right? Yeah, therefore I want to ask in the future for real application, how can you combine 3D and 2D material to get real application of this kind of perovskite solar cells? Yeah.
Okay, the first question about the mechanism of the recovery in the performance, it came out, as I explained, since it's a mesoporous structure, which means that the perovskite is really inside a very small pores of materials. Once you degrade, you have some degradation, which means that the precursor are taken apart, or let's say the distance between them is increasing. But then they are staying in the night for around 12 or 20 hours. And due to the close proximity of those precursors, they are really reacting again and forming perovskite. And this is not so obvious since you don't have solvents there. But this is really a solid state reaction. And we also proved it when you take a powder of perovskite from one side of one precursor and the other precursor of powder, and you just grind them together, you create a new perovskite. Yeah. So the flexibility of the material allow you to do that, okay, even without solvents. So this is for the recovery mechanism. The other one for the low dimensional, I agree. I mean, this is really, we worked on it. We are working on it like in the last 3 to 4 years. And this is very attractive since you have almost infinity batch number of materials that you can make out of them. Still, we are looking for the one that can perform as well as the 3-dimensional and still show the better stability. At the moment, I agree, it's a little bit lower than the 3-dimensional, but on the other hand, if you look on the 3-dimensional devices, the highest one are not surviving for a long time. They are giving very nice efficiency, but finally, the stability of them is really bad. So even if you are paying, let's say 2-3% in efficiency, but you get something that work for much longer time, I think it works, at least for us.
Yeah,
okay.
Thank you.
You're welcome. I think there is another question in Q&A.
Okay, sorry.
From Eud Kainan.
What would happen if you add a highlight scavenger? Will that lead also to low dimensionality? That's the question from the audience.
Yeah, this is a good question. Usually the low dimensionality create just when the solvent evaporates in the solid state, which means that the scavenger, usually if you put it in the solution, it's a good question. We didn't write. The question, what will happen once you're putting on the surface and everything evaporates there? If it's really be effective or it's already killing everything in the solution. But good question, Udi. Yeah, something else? No, I don't see.
Okay, so I'll just say a few words and then we'll move to the discussion panel and Professor Uri Banin will head this. So first I want to thank all the speakers of this session. It was a very interesting one and I think we kind of covered different types of nanomaterials that are involved in major parts now of sustainable energy research and alternative fuels. I think that, you know, we are in an interesting timing. We are only a few days after there was this International Leaders Summit on Climate. I think it was organized by the new US president. So we heard in the news almost every country declaring very ambitious commitments to reducing carbon emissions within the next 10, 20, 30 years. And I guess that the topic of this session is very relevant, maybe on working on making something like that possibly happen. So I think that both our countries have a lot of activity and very successful research in this direction. So I think this is really a timely session on this topic. And I guess it will be interesting also maybe to discuss this idea, these directions in the discussion panel. So thank you again to all speakers and let's move to the panel. Uri, if you want to start.
Sure, I will ask all the panelists, start your cameras, please. I'd like to ask first especially to Professor Wei and Professor Edgar about what do you think are the challenges and the opportunities in solar photovoltaics for combining with nano concepts, or anyone else who wants to comment on this, but I think we can direct this first to Professor Wei and Professor Edgar. Which one want to start?
Yes,
please,
maybe
Professor.
I start first.
Yes, please.
Okay, yeah. Actually, I think nanotechnology, can really contribute to the solar cell technology a lot, because actually traditional the silicon using single crystal and then doing the fabrication. But all this nanotechnology perovskite solar cells, organic solar cells, be based on the solution process. With this one, actually, sorry, actually their cost, yeah, actually will be much lower than traditional silicon technology. But however, recently, you know, the price of the silicon solar cells decreased a lot. Yeah, especially because of the Chinese production manufacturing is being proceeded with single crystal, multi-crystal silicon with really low cost, actually lower than the coal burning electricity. Yeah, therefore I think for both technology, maybe one actually they may find some complementary using areas different from silicon technology. The second one, I think maybe a good direction for perovskite solar cells. They are doing some tandem solar cells, maybe showing higher efficiency than just using one material. Therefore, I think, yeah, for the solar cell, actually the most important one is efficiency and then the stability. I think the perovskite solar cells are already quite good in the efficiency and showing some promising results for the stability improvement. But for organic solar cells, we're doing quite good in the last several years, but the efficiency is still lower than this kind of the perovskite and silicon. But I think in the future, it's showing the promising progress, give us the confidence. Actually, in China, I know several groups have shown the organic solar cell can reach in the efficiency 19 to 20%. I think really approaching higher than 20%. And also stability is another concern. Yeah, is this kind of nanostructure stable or not? Yeah, it depending on the material and depending on the manufacturing technology and also depending on the encapsulation. Therefore, I think for the new technology for these solar cells, we do have the chance, but still we need to optimize the system better to meet the requirement for industry. Yes, that's my comments. Yeah.
Thank you very much. Lioz, you want to add something?
Yeah, I think I will go back to your question about the nanotechnology, or let's say nanomaterials in the solar cells. I demonstrate in my last two topics how we can use nanostructures, if it's the carbon cells or the ITO cells, and this is the advantage. This is the advantage of using nanomaterials, and this is, I think, different to the current technologies, mainly the silicon, which do not use those kind of things. And finally, this nanomaterials can really assist in, or of course, increasing the surface area. This is something obvious, but we demonstrate how it can help for the stability, for example, how you can create a much easier structure of the solar cell just by printing the layers, even the contact, and then you drop the perovskite through the mesopore structure. And if I go back to, like Professor Yi said, in terms of commercialization, yeah, perovskite still needs to, still has some things that he has to cross through the way, mainly the stability. But I think it's on the way, since a lot of researchers today are in this direction. And like any technology, it takes a little bit time. And it's important. It's important to say that the silicon is the only one is there. It's not good. You always need to think, to the future, what will be if you stay with the silicon, so we can close everything here and go home.
Thank you very much, Lioz. And I'd also like now to ask Avner and Dongfeng about the kind of challenges and opportunities in the catalysis, electrocatalysis, and also photocatalysis, all related to catalysis with nanostructures. How do you see these opportunities and challenges in these areas? Which one wants to start? Avner, you want to start? Or Hongfeng, please, Professor Yin.
Okay. I think currently the traditional catalysis have some challenge because of efficiency, because of the selectivity, may come to a problem. Nanomaterials application in catalysis is a pretty good way for the catalysis, and also because considering current the hydrogen production, especially for the green hydrogen production, the electrocatalysis is a very hot area because it can use like other energy, for example, the wind, water-powered, solar-based electricity, and so electrocatalysis will be currently is very hot and will also be will have a great application in catalysis, and that's also a good trend for catalysis.
Thank you very much. Avner, you want to add something or comment?
Yes, I think it also ties into the question you introduced before. I think that catalysis and photocatalysis are closely tied to solar cells because one of the major issues towards greater utilization of solar energy is the issue of storage, and I think that's very clear. Yes, I mean, on average, the number of solar hours, even in countries such as Israel, where we have a lot of sunshine, or photovoltaic usable solar hours, is 4 to 5 hours a day on average. So it means, you need to store a lot of energy if you want to rely on solar energy, and similar calculation also apply to wind energy. So the issue of storage is extremely important to allow deeper penetration of solar and wind energy to the grid, and it's not just power, okay? It's not just power production, it's also other application that we need. There is a lot of energy that goes into other sectors, such as transportation, heating, etc. So I think that, there is strong connection between catalysis that generate fuels, either hydrogen or hydrocarbon fuels, and there the connection to nanotechnology I think is pretty obvious. Yeah, I mean, catalysis, but by nature occur the interface between two different media, between solid medium and gas or liquid medium. So it's interfacial phenomena. So it's basically a challenge of surface to volume kind of question on the very basic looking at the problem. And their nanomaterials, they obviously the way to go. So that's very simplistic viewpoint. I mean, the individual challenges are very different, okay? So every problem would have its unique issues and its unique solutions. But I think the linkage to nanotechnology in general is there because it's a challenge of surface to volume kind of problem.
Thank you very much. And what we witness now, let's say in daily life, is that there is a very large penetration of electrical vehicles now. In Israel, for example, we have several Chinese makers, by the way, that are now selling electric cars in Israel. Tesla just started selling electric cars in Israel. Israel is actually a small country that electric car seems like an interesting solution for transportation. On the other hand, we heard about possibly fuel cell technologies. And I would like to open a question about this near future and farther down the line, the balance or the issue of electrical versus fuel cell, electrical battery powered, versus fuel cell powered electrical cars or electrical transportation. If anyone would like to comment on that, please. Again, Avner, you maybe want to start. I think you are.
Yeah, I'm happy to share what I've learned in the past, couple of years since I've been involved in the company. Then, we look a lot at markets, okay? What are the future markets for hydrogen, for green hydrogen? Actually, I don't want to kind of break your spirit, but actually the transport sector for hydrogen seems like not very promising, to say the least, okay? Almost to the level that now in my company and in other companies that look at electrolysis technology is no more than entry market, okay? So, you know, even if you think that there will be a large segment of hydrogen-based electric vehicle, you know, you're looking at number of hydrogen refueling stations in the several thousands at maximum. That's not a huge market, okay? That's not the dream. The dream is into much, much, much larger markets, industrial markets that are currently, you know, on gigawatt scale. So think about petrochemical industry, okay? Petrochemical industries or petrochemical plants are gigawatt scale plants. And that's actually the kind of market that, that we are looking towards. And it's not just us, okay? If you look what goes on in the green hydrogen community, they now talk about tens of megawatt plants and hundreds of megawatt plants. And there are also programs, there is a plan actually in Saudi Arabia in the new science city of Neom. They kind of build a plan to interface a 5 gigawatt solar plant to a 2 gigawatt electrolysis plant. So this is the scale that the hydrogen industry is looking at. It's not there yet, okay, but that's what it's looking at. And that's much more than transportation alone, okay? Specifically for transportation, I think that the battery electric vehicles they give really good solution to small size cars and to passenger cars, etc. Currently, there is still an issue. I don't think that currently they can give solution to trucks and heavy duty transportation. So, you know, currently, I believe, you know, it's about 50-50, maybe even more for a battery electric vehicle. And maybe 60% of the future market will be by battery electric vehicle and maybe 40% by fuel cell electric vehicles, which will capture more of the large scale vehicles, yeah, like trucks and more.
Thank you very much, Avner. I would like to open now the opportunity for our chairs and for Professor Willner, if you have any comments on this connection of nano and energy and what the future holds ahead in this area of connection of nano and energy. If you have any comments or thoughts to share. Itamar?
Well, I thought that Gil and our Chinese co-chair will be before me, and I will finish the...
So wait.
That's the way, so maybe it's a message to me that
sure.
have to terminate this conference. In fact, I would say that I'm not far away from this field of energy conversion and generation of alternative fuels. And I followed this area, I would say, in the last 40, 50 years, since I was a postdoc in Calvin's laboratory at Berkeley, where he praised photosynthesis as the source of the future energy for the world. Now, I really think that nanotechnology advanced the field of energy conversion, photocatalysis, electrocatalysis, and sustainable energy resources. But if we look as an integrated, I mean, from a scientific point of view, I cannot comment about what Avner, he moves big trucks and moves the traffic worldwide. I don't think that I'm an expert here, but I think that we made tremendous advances in the field of energy conversion, and nanotechnology and nanomaterials played a major role. But if we look carefully at the problems, I think that major challenges are still ahead of us. And there is not something that I can say that we have the ultimate solution to the problem. Stability, as Leo's, and I followed all the talks today during this morning session, stability is definitely an important issue. The toxicity of the materials, of the nanomaterials that we are using, and the environmental consequences of such nanomaterials for the universe are certainly a problem. The issue of transportation and packaging, as Avner mentioned, is certainly a problem that needs to be resolved, and hydrogen here is a major concern, how big volumes of the hydrogen will be transported. And the safety is also an issue that certainly is a problem. We are witnessing already in these weeks and these times this Tesla car that exploded, and the shares of Tesla dropped and crashed because of one lousy lousy failure, but the safety will certainly accompany the issue of energy concerns and of the contributions of nanomaterials. Last but not least is the issue of cost effectiveness. And I think that this is something that we as basic scientists, maybe Avner, and he will say he can more evaluate the cost effectiveness of what we are doing, but we overlook very often what is the cost of the final unit of energy that we get out from a certain material, from a certain device. And businessmen and industries will always ask this as the bottom question. And I think that here we don't have definite answers, but we have to pursue and to invest a lot of efforts to address all these issues that were discussed here. And I think that nanomaterials, nanotechnology has a lot of promises and could provide many of the answers to these questions. Yet I think that we have also to look to other niches that are related to the field. And Uri mentioned the photocatalysis, electrocatalysis. And I think that here we need more efforts. For example, fine chemicals where the cost effectiveness is not such a question, and if we have a good catalyst that responds to everything, if we get a very valuable chemical out of these materials, then it is a relatively short-term goal that can be a contribution of the field. The second thing relates to the environmental issues and the contribution of nanomaterials, not only to provide green sources, and I think that here we emphasized all the time, and when we defined at our discussions with the Academy of China and our academy, how to call this subtopic, we defined this as energy and environment. And these are two interlinked issues that are very important. And even in our discussion here today, we were talking a lot about the green resources and the alternative green resources. But I think that photocatalysis should play a very, very important role also in the degradation of pollutants. And this was a field that attracted a lot of interest 10 years ago. Unfortunately, lately it declined. But here, I think that photocatalysis and electrocatalysis can add an additional dimensions to all these links of energy, environment, and the future of our universe. And it is definitely our duty to advance this field. And I am very optimistic that we are on the way. I think that I would like to thank all the speakers of the day. It was a wonderful opportunity today and excellent talks from everybody. I can only regret that we didn't have many other talks of this quality, that we can have 2 days discussions or 3 days discussion on this topic. So thanks very much the speakers, thank the moderator, the chairman, and all the organizers. It was a wonderful conference. Thank you.
Thank you.
Thank you.
Thank you very much.
Yeah, good.
Thank you.
Thank you.
Bye.
Bye
Bye-bye.
bye.
Bye.
Bye bye.
Bye.